The slide presentation I wanted to first put on before I start discussing, that's a little bit of hiccups, I think, initial that normally happens. What is the basic difference? In fact, it's a really problematic still. This There are some issues in this particular right now. What are the basic, you can say, modifications? It's a little a bit of, I mean, I think again, a little bit of delays, but initial, you can say, system based, some hiccups. The slides are visible now. Hello, students.
Yes, sir.
Oh, good. Thank you. I think it has taken a little bit of time, but anyway, I think what we were discussing about, you can say, minimum shift keying and how this minimum shift keying is different than, you can say, QPSK. So QPSK, you can say, quadrature phase shift keying, that we have already studied about. So what are the basic difference between MSK and QPSK, and why we want to have a, let's say, better scheme than QPSK? The motivation is that because if you look at the spectrum of a QPSK system, then I mean, if you look at the transitions also, I must be, yeah, like this, these are the slides. I mean, you can look at, if you have your basement signal, let's say B1, B2, B3, B4, B5, B6, like that, and then you have B odd. That means my odd bits is staying here for, you can say, 2 bits, and similarly my even bit is also staying for 2 bits. But if you look at, this particular, you can say, transition. Now, this transition means essentially the variation, abrupt, you can say, variation. That means from high to low, it is going, you can say, down. And at least in your other systems also, signals and system, you must have studied, like step functions or, other kind of system responses where the transition is very rapid. They lead to, you can say, they introduce some, you can say, higher frequency components in the system. Now, what does it mean by high frequency component system? It means essentially, if you look at this spectrum of this particular, let's say this 2-bit B odd pulse, then this is obviously, all of you know it, that this is a sync pulse, sync function. Now, this sync function, when multiplied by the carrier, it will have you can say, formulation something like this. This is G stands for power spectral density, you can call here offset, offset QPSK in, let's say, in frequency domain, and this EB is your bit energy, and this, look here, sine 2 pi f minus f0 upon fb. So this f0 is your carrier. So what is the kind of spectrum that you are transmitting, or the kind of signal that your modulated signal you can call for a QPSK system is like something like this thing. Now, this is the original statement. So what is the problem you can see in this system is, when we have, you can say, number of users. So let's say one user is occupying one channel, another user is occupying another channel. Then these particular high frequency components may lead to, you can say, what is called co-channel interference. Co-channel interference means essentially you are listening to the communication of your, adjacent speaker also, and that's not, you can say, desirable as far as communication systems are concerned. So what has, what was thought was how to get over this problem, and to get over this problem, I think what was thought of was, you can say, this abrupt variations, if you can, minimize, or somewhere some continuity if you can ensure, then perhaps this particular phase type of, problem will not be there in the system. So essentially, you can say, MSK differs in 2, you can say, major features as far as QPSK is concerned. That's a central lobe. Central lobe, mostly, you understand, central lobe in a sync function. this contains, you can say, I mean, total power contained about 90 to 95%. So that's a little bit bigger in case of, you can say, MSK, almost 1.5 times. And secondly, the property is phase continuity. Phase continuity means from one transition to another transition. If you look in MSK, there is no such abrupt phase variations. Okay, so why? I mean, if you look at this particular diagram here, what is done? I mean, this is QPSK. I think each student understand. So how do we modify it? We modify it by multiplying this particular, you can say, B0 or B, you can say odd, these functions by some functions which you can call as sine 2 pi t upon 4, that, I mean, a particular time period. Similarly, cos 2 pi t upon 4 pi, I mean, TB. So essentially, you can say for B odd, let us say we go for B odd corresponding to, if you look at, your sine, you can say, if your even, bit, we are, even bit is getting multiplied by the sine sine function, and your, you can say, odd multiple, bit, that is getting multiplied by the cos function. Why it is, and what is the consequence of that? Try to understand that. So suppose what you can see here, if this is my B0, okay, I mean, all students can see the slides.
Yes, sir.
Okay, thanks. Like B0, now look at B0, I'm multiplying my odd bits, I'm multiplying by, let's say, my cos, function. So cos function, if you look at here, this dotted particular line is cos function. So if you extend it to like this one, you can, I mean, extend it up to this particular also. But if you see here, B odd, if you multiply this particular with this function, so what might, you can say, B odd multiplied by cos functions. So essentially, if you look at those particular products, you can see this is my odd bit. Okay, so this is high here, this is high here, so this is high here, you can say, corresponding to my B odd. Okay, considering this, if you extend it to in this region also, then this particular will be, you can say, will be multiplied by, you can say, my B odd bit this here, so both are positive. So this essentially becomes a particular, you can say, you can call as a half part of, your sinusoidal behavior. Okay, so this becomes my B1. Now then comes the B3. Let's say this B3 is, you can see here, B3 is negative, or that means, let's say, 0. I hope you understand the polar representation. So this B3, when you multiply by this particular cos function, look here, this B3 is negative, and this cos is also negative. This B3 is negative, cos is negative, so both of them give you positive. Okay, so that's why I get another B3 positive. Likewise, if you look at B5, you can do that. Similarly, for, you can say, even also, what you can do essentially is, B1 we are multiplying by the sine function. So look at this sine function here. Sine function is this one, you can say, corresponding to, and if you look at the, corresponding to B1, this is my high here, this is high here, so this should be high here, you can say, corresponding to even also. Understand? Or any student has any doubt? So what I have converted, you can say, I have converted my, you can say, this rectangular or abrupt transitions to a continuously varying, can say, a particular function. Now you can continually vary this particular. Okay, so, I mean, this particular, you might say that how does it benefit? We'll see that this benefits in a way, because this can ensure phase continuity. How? We will see that. And what happens, you can say, corresponding to, if you look at here, I mean, the two frequency component, omega 0 plus sigma upon 2 pi, omega 0 minus sigma upon 2 pi. I mean, two carriers that essentially we are using to transmit our, you can say, B0 and, I mean, even and odd bits. So essentially, you can see here, if this particular, they combine together, you can see, if I say omega 0 sigma upon 2 pi, so what I essentially, let's say this is 1.25 FB, that means 1.5 FB. So I'm transmitting this particular carrier, and if you look at, if you look at this particular B0 and B odd combination here, that means the bits I'm transmitting, you know, in QPSK there are 4 symbols. So let's say for this particular, combination of, I mean, you can say combination of this particular 1 that will be transmitted through my this carrier. Okay, now, I mean, you can say one will be cos, another will be sine, or another will be opposite to that. You can say polarity as far as that is concerned. So likewise, I mean, if I am transmitting, let's say, My B odd is -1 and B even is, let's say, 1. So I'll be transmitting this kind of carrier, you can say, corresponding to. So rather than any abrupt variations I'm transmitting now, you can say corresponding to my this particular way, what you can call them essentially is frequency, carriers. They are, you can say, carrying forward my information. -1, I'll transmit, you can see this kind of resultant, you can see carrier. -1, or -1, I mean, like all combinations, all four combinations. How many combinations? Four symbols. Since you are transmitting four symbols, so four symbols essentially means, I mean, you can see cos positive, cos negative, cos positive, or sine positive and sine negative in one or other frequency component. Understand? You understand? I mean, at least, this particular, you can say, transmission in an MSK, that ensures that I am transmitting, you can say, different frequency component for different, you can say, combination of the symbols. Now look here, I mean, this more explained also as we were talking. So how do I represent my MSK signal? My MSK signal will be represented by √2 PS, that you in any case, power component, B even bit, and my sine phasor I'm multiplying to modify, you can say, and to smooth out the edges, you can call it. So this is my sine 2 pi t upon 4 dB. I mean, that's a time period where I'm taking for that. And cos omega 0 is my carrier. So my B1 obviously is carried forward by the cos along with this particular. So, and the next one is B odd cos 2 pi as a carrier and sine omega 0 t as your, you can say, carrier. Now, if you do a little bit of, you can say, mathematics here, this is sine A cos B. Okay. Sine A cos B. Similarly here cos A sine B. So you can convert into this form, you can say √2 PS B0 t plus BET upon 2 sine omega 0 plus sigma t, √2 PS B0 t minus BET upon 2 sine omega 0 minus sigma t. Look here, there are two carriers, omega 0 plus sigma and sine omega 0 minus sigma. Okay, two carrier frequencies, you can call them corresponding to. So the representation, you can say, corresponding essentially is B0 plus BET. Now you might say, I mean, it can be further simplified. You can say symbols, how do I define my symbols here? What is my sigma? Sigma is equal to 2 pi upon 4 TB. That means 2 pi and TB FB by 4. TB is my, you can say, bit interval. Now, if you define this particular as CH, okay, C high, let us say, because it's a positive. So B0 plus BET is divided by 2. If I write this as CH, and CL is B0 minus B2 upon T, and omega H is omega 0, and omega L is this thing. So what representation finally comes out of MSK is √2 PS CHT sine omega HT, √2 PS CLT sine omega HT. Now you can see here FH is F0 plus FB by 2 and FL is F0 minus F by 2. That's the interval. So I will be transmitting, you can say, corresponding to FH this frequency and FL to some integral multiple of FB by 4, you can say, corresponding. Now what is a point that you should try to understand, like, I mean, what is the CH and CL? If you look at this, if you look at the geometric, representation or signal space representation of my MSK signal. So what are the two carriers I have? I have two carriers as sine omega H, sine omega L. Look, they are orthogonal. Okay, that's a minimum interval that we take so that they can be converted to orthogonality. Now look here on this axis, if you look at, if I say that this my, CH is equal to 1. CH is equal to 1 means what? When it can 1? When B odd is 1 and B, you can say, even is also 1. So 1 plus 1 upon 2. So CH can be 1, you can call. Similarly, if CH is equal to 1, CL will be equal to 0. Why? Because B0 minus, that's what the, you can say, representation is there. Sorry, this is a little bit unstable. A little bit of unstable, but I think it will become probably, yes. The system related problems. Anyway, so I mean, what essentially I was trying to explain is this particular, say, CH is equal to 1, CL is equal to 0. So if CH is equal to 1, then B0 and B odd will be 1. I mean, 1 minus 1 is 0. So that means CL is equal to 0. Similarly, if you look at CL, if CL is equal to 1, that means both of them, you can say corresponding to negative, okay? Corresponding to negative, both of them, or one is, you can say, corresponding to negative. CL is equal to 1 will be when your this particular, B0 minus BT is equal to, you can say, corresponding to 1. And when it can be, you can say corresponding to, we can let us say we can analyze the corresponding situation. When the CL will be equal to 1, CH has to be 0, because obviously one of them will be opposite to that. So B0 minus B1 will be 0. Understand? Similarly, CH will be negative. When it will be negative, when both of negative, you can say B0 and B odd are both negative. That means -1, that symbol. For that symbol, it will be CH is equal to -1. And corresponding to, you can say, CL is equal to -1 when, I mean, 1 -1 combination, you can say, B0, B odd, you can say both of them are negative. So that will be corresponding to CL is equal to -1. Is it clear? The signal space representation for MSK signal. This is, you can say, my orthonormal function, you can say, function. That's a √2 ps sine omega lt, and this is 2 upon √2 s sine omega ht. So this is the orthogonal representation for my MSK signal. Any question you want to ask? Yes, students. The next property that I want to, or perhaps the important property, is what is called MSK, phase continuity. What is a phase continuity? Phase continuity, essentially, if you plot, you can say corresponding to, I mean, my phi plus and phi minus omega 0 plus sigma t, omega ht, and phi minus omega 0 minus sigma t. So why, I mean, you can see here, because look here, I mean, you know very well that at TB interval, one of the B0 or B odd can change. Similarly, for the next bit, either it's even and odd. Suppose at odd, I mean, you can say odd bit is changing. So that means, let's say, pi phase difference is there. At even it is taking, then it's a 2 pi, phase difference. At 3, it's a 3 pi, 4 pi, 5 pi. I mean, even and odd, you can call them. Okay. So corresponding to, I mean, look here. I mean, that's what I was trying to explain you, that -1, I'll be, you can say, transmitting minus sine omega 0 plus sigma t. Let us say, I mean, 4 symbols. For B1 -1 and B odd 1, I will be transmitting sine omega 0 minus sigma t. 1 -1 minus sine omega 0 minus sigma t. And similarly, for 1 I will be transmitting sine omega 0 plus sigma t. So that means, you can say all the 4 symbols are having some frequency. Of course, you can convert them to sine also, I mean, as and when required. But in terms of sine, you can represent, one will be lower, you can say, like you can see here, -1 1 and 1 -1 corresponding to lower frequency, -1 and 1 1 corresponding to higher frequency component. As far as the phase continuity is concerned, now if you plot, you can say corresponding to, I mean, this particular response to my, I mean, different carriers. And if you plot here, phase is on the y-axis, and here it's a time interval. So what is happening here, at this particular, TB, the phase change is pi, and here the phase change essentially is 2 pi. So if the phase change is 2 pi, there is no problem, because essentially 2 pi means what, as you have studied in your oscillators also. So 2 pi means essentially the same phase, it's a 0, or you can say corresponding to, I mean, the same phase that the two signal will have. If 2 pi, they are different, you can say separated by 2 pi. So if I write my MSK equation, then I can, I mean, for corresponding to the phase variation, I can write my this MSK equation as to be B0t √2 ps sine omega 0t plus B0 B sigma t. I mean, I can represent my MSK in you can say, in this reduced form, to study about the phase. So look here, how the phase is, you can say, corresponding, getting modified for corresponding to this particular sinusoidal. Omega 0 is no problem. Obviously, the phase will be obviously varied by B0 and BT. I mean, depending upon their 1 or 1 -1, whatever the combination they have. Sigma t is the phase shift, because that's where the higher and lower frequency will be picked up, and T. So this particular expression represents, you can see, this phase variation. Now, what we can make out of this particular expression is, if you look at this phase expression, like look here, if what is phi plus omega 0 plus sigma t, so B0 BT, that has to be positive. Okay, and for phi minus omega 0 minus sigma t, B0 BT has to be minus, I mean, is -1. Now, if you look at this equation, now what we can make out from this equation is, suppose you can say my, phase change is 2 pi. phase change is 2 pi, that means it has hardly any effect on it, you can say, corresponding to, because the phase is changing by 2 pi. The problem is with you can say odd change, odd change that you can say corresponding to the signal I'm transmitting. So look here, if I'm having, you can see, this particular odd transmission or phase change, it's changing by pi. And now what is happening? This pi, you can say, and this b0 to pi, this will also introduce, you can say, corresponding to my pi phase, and this pi is, you can say, corresponding to my this particular response. So pi plus pi, this becomes again 2 pi. Okay, understand? So for, you can say, even it is obvious that it's changing by 2 pi, and for odd, if it's changing by pi, the another pi, you can say, I can introduce in terms of this b0 t. So again the phase remains 2 pi. What does it mean? It means essentially phase continuity. That means that phase, abrupt phase change, the problem that we had in our earlier, you can say, system, is not going to be there in as far as this particular, you can say, minimum shift keying is concerned. And that's a big relief, you can say. And that's why I said in case of GSM, they picked up Gaussian, GMS, Gaussian minimum shift keying. Gaussian means essentially, you can say, your pulse shape, you can give it to some sort of Gaussian. MSK, of course, is the same, you can say, corresponding. So that's what, the corresponding to this is. Yes, any question or anything not clear, students? And this is where, as you can see, power spectral density. Power spectral density, if you look at, this is, let's say, offset QPSK, and this is my QPSK corresponding to, okay? I mean, both of them I'm representing as together, and another one is corresponding to MSK. So, I mean, by now, I think you can appreciate it, that power spectral component or power distribution, across the frequency is the biggest, you can say, perhaps you can say, the parameter that every, designer has to focus on, because how much power you are transmitting, at what frequency you are transmitting, so that, I mean, co-channel interference can be reduced, or some other, you can say, power, consumption issues can be negotiated. And so I think everyone can pick it up, this QPSK. So in QPSK, if you look at a QPSK corresponding variation, I have, you can say, on vertical axis I am plotting, this is EB, dB. In terms of dB, I am plotting, let us say, 0 to minus dB, or and to positive. So like you can see here, I mean, this particular has a lot of side lobes, you can say. Why the side lobes? Side lobes, because if you look at sine omega, that component, you can say, corresponding to our, sync function also, then you will have some carriers, I mean, side adjacent, side lobes also you have. Understand? These are the side lobes. If you look at the MSK, the central lobe is bigger one, you can see here. If this is corresponding to MSK, so if you look at this MSK, your central lobe here, this central lobe, this is for QPSK, this is for MSK. So the central lobe width is much, you can say, bigger in case of MSK. That's almost 1.5 times. And the side lobes are also reduced here. Look here. So that's in terms of power also, you can see here. Now, if you look at this particular, baseband waveform, I mean, this in QPSK, then we can represent this particular, power spectral density component mathematically in this form. And this is F by FB. I mean, you can see my corresponding to my frequency variation, because power spectral density we plot. What is the meaning of power spectral density? Power spectral density essentially means distribution of the power across the frequencies. So at different frequencies, you can say F by FB ratio, if let's say 0.5, what it will be at 1 point, at 1.5, at 2, or whatever corresponding ratio you define. Now, if you write a general expression for GMSK for its power spectral density, you might say that why power spectral density is important. Power spectral density, in fact, most critical component nowadays, not only in terms of, you can say, extending the, you can say, your battery capacities, because you don't want to dissipate it, as soon as, if you consume more power, obviously the battery will get discharged much sooner, you can say. So the focus for a, communication designer now is to reduce power consumption, and looking to the, you can say, radiation effects, looking to the environmental, this global warming or other issues. If you always, I mean, if any signal that is going in the, you can say, if you can reduce the power, I think each one of you are now probably familiar with this carbon emissions or warming of the environment, you can say corresponding to our atmosphere, that obviously has a lot of consequences. So power, if you can transmit it the minimum, that is always much better. So this is what this power aspect. You might say that in the very beginning I said how QPSK is different than MSK. So one aspect is this one. Central lobe, you can say, has much bigger power, you can say here. So I don't have to bother much about, but the power level that I am trying to transmit, because about sync function, that we are only concerned about the central lobe. Like in the Nyquist pulse criteria also we have studied that this is 1 at, you can say, for all other time intervals I wanted this value to be 0, and the side lobes also reduced to be minimum. So that's what. Now how do we generate it? Let's say QPSK signal. Okay, so what kind of modulator we need to have? So how do you generate? What we have is sine omega 0 t, I think, as a carrier, and then the cos sigma t. That's what the shift that we already know about. What is the minimum, you can say, difference corresponding to these carriers. Now, what we do essentially sine A cos B, let us say. So this combination can be band pass filter. I have to band pass filter omega 0 corresponding to plus sigma and omega minus corresponding to sigma, you can say. So one band pass filter will produce sine omega 0 plus sigma, another will produce corresponding to here sine omega 0 minus sigma t. You can understand A cos B. What we do essentially this one, we put up to some adder here, this particular harmonic, you can see, output here, and this output here I add up, I put it to adder, and I put here it as to a subtractor. So what a adder gives me output is xt cos sigma t sin omega 0 t, and this particular subtractor gives me sin sigma t cos omega 0 t. You know very well, we need to have, you can say, corresponding to two, this particular sinusoid or cosine component to gate over the, you can say, abrupt edges of the baseband signal. So that's what we are trying to produce, you can say, corresponding to here. What we do here is we are multiplying by some even, you can say, corresponding to bit here, and this to odd bit here, and then we add them together, and what we get essentially is our minimum shift keying signal. I think it's very simple. Generation is very simple, at least. Now, many times, if you must have read that, side bands can be suppressed by low. These are the problems in communication. I think you must have done in other, subjects also. Suppose I pass a signal which is having a sideband through a filter. What will happen? It will suppress them. If it suppresses them in frequency domain, you can say you will have a time domain, expansion. So solutions are not, you can say, corresponding to, to implement solutions is not so easy, and particularly, high speed, this communication, this becomes even much, you can say. So the filter design or other issues, I think, perhaps I don't know how much you have probably gone through that, but know a little bit about, like, how the band pass filter is characterized, how it's an amplitude variation, how it's, you can say, phase variations take place, in analog and as well as in digital domain. And once we get this particular, how do we recover back? What we do essentially is, because this is a synchronous demodulation, you can call it. So I generate xt and yt. What is xt yt? Xt yt I generate, if this is my MSK, again I square it up, the signal, the same thing, you can say, ch square sin square, cl square sin square. So this is, my component here. I again pass it to, you can say, band pass filter, to a band pass filter which is centered around 2 megaL, divide by 2, and what I get essentially, look here, this output here is ps sin 2 omega ht, and if I divide it by 2, this becomes 1 by 2 sin omega ht here. Similarly here, if I divide it by 2, I get essentially half omega lt. What I do with this particular carriers is I again subtract them to add and subtractor, and this is particular my filter and amplifier. Now this is my recovered carrier. Okay, this is my recovered carrier, you can say, which this is my x. Oh, this is my x and this is my y, and here I'm getting my carrier back, you can say, corresponding to. So this is xt and yt, a combination of, you can say, corresponding to this omega h and omega l, and this is what I'm using sin xt and yt here. So I multiply, you can say, one incoming signal with xt, another incoming signal with yt. This gives me B0T and BET, and then what I do, I essentially odd bit means 2k minus 1 to 2k plus 1. That means odd bits. 2 TB is interval. So 2k minus 1 to 2k plus 1. So you can say integrate it, pass through. I mean that we have already studied about integrator and dump circuit. So, and similarly here, this is for even bit. So I sample at the even interval here. I sample at the odd interval here. I store the samples, and then I have a switch here which keeps on alternating between these two, you can say, contacts. One time it will sample my even, another time it may sample my odd bit. Okay, so this is what, a simple, you can say, demodulating circuit of a MSK. Any student has any question? Okay, so this is about, corresponding to what I wanted to cover about my digital modulation. The other topic we can, I think, start. Still, there is some time. I want to start now about some receiver. I think I want to do. If we can have a receiver, how do you recover back, this particular, you can say, signals? Now, yes, uh, is it is it visible to everyone, students? Please.
Yes, sir.
Yeah, please confirm. Yes. Okay. So next topic I want to start with is optimal reception of digital signals, because now we have talked about, modulation. So how do we receive the signal back, and what are the different considerations in gating, you can say, my optical reception? And so if you talk about, let's say, baseband signal receiver, I think the basic principle of a baseband signal receiver is, if suppose I'm transmitting a baseband signal, look at this particular signal, you can say any binary signal that we want to transmit. Now, this is, let's say, my high, input, any. And what is happening here is the noise, how the noise can affect this particular amplitude, let's say. This may be, you can say, smaller here, but at some interval, it may be very big enough so that this positive becomes negative here. Okay. So how noise may cause, you can say, an error in the determination of transmitted voltage signal levels. That's what we want to understand now. And this particular receiver, we have already studied about that integrator and dump circuit. That's a dump switch. Dump switch essentially means, you can say, you have to discharge this capacitor to get it charged again, you can say. And that's my sampling switch, which I am sampling, you can say. So if this is my input here, this input gets, you can say, corrupted by noise, and noise is white Gaussian noise, which is random. I normally say white Gaussian has a power spectral density that eta by 2. And so when this, you can say, get added up, that's what gets fed to my receiver part. I gain amplifier I'll have corresponding to, and then this integrator. I think all of you are familiar with that. So suppose, if suppose this is my input here, let's say this is my out, you can say, corresponding to output signal, integrate and dump, you can say, integrate and this thing, negative, positive. So because of the noise, this can, result into error. Now we want to study it about, let's say, if you have a tau is equal to RC, if it is a RC network, so V0T is what? 1 upon tau, 0 to T, ST plus NTT. That's very simple, because we have a signal, we have the noise, and that's what our integrator is doing. It will integrate, you can say. So if it integrates my signal generates some finite output voltage. Okay. So finite output voltage I can write as S0T as 1 upon tau, 0 to T, Vt. So that means Vt upon tau. No problem. You are simply integrating VDT. V is, let's say, constant voltage level. So this becomes essentially T upon tau. 0 to T interval is there. So this Vt upon tau, no issue. Now this N0T also generate, you can say, corresponding NTT dt. Now there is a problem here because NT is not a, you can say, constant voltage here. It's a random signal. So for random signal, you have to talk about the variance of this particular. Okay. So if you find the variance of this N0T, why N0T we are calling? Because we are sampling it at the time interval T, you can say, corresponding. So this variance sigma 0 square, that's N0, I mean square T, that I can write as eta T 2 upon 2T square at the same interval as I am sampling my signal. So what the noise, you can say, integrator is producing this much of the noise, let's say, corresponding to the noise input signal. So the relationship between this output voltage that being produced by my, you can say, desirable signal, and this is my, you can say, noise signal. So how do they, at least work together, or you can say, essentially, noise creates, how noise can create problem for the output signal. So what is my output? Output my is S0T plus N0T. And if you define a figure of merit, what is a figure of merit? Figure of merit means signal power upon noise power. So if you define the noise signal power upon noise power, this becomes essentially 2 upon eta V square T. Okay, so we can calculate here. I mean, what particular, parameter will, you can say, increase this figure of merit means essentially quality, you can call. Now you might say that what is the problem with this noise? I mean, where this noise can create the problem, and that's where we need to understand this particular, because as I said, signal is random, and we see that this particular noise has a Gaussian property. I mean, it you can say follows the Gaussian distribution function. So if I plot Gaussian distributions, for the noise, you can say corresponding to, and then I can write this Fn0t as e to the power minus n0 square t upon 2 sigma 0 square upon 2 pi sigma 0 square. Every student understands, I think, this Gaussian, the probability density function. Yes or no? You understand this particular, or appreciate this particular Gaussian probability density function?
Okay.
Yes, sir.
Okay, good. So if you look at this particular graph, this where this noise can produce problem, because the let's say I have a, you can say, corresponding to, let's say, for corresponding to negative, when negative can become positive. Negative can become positive when obviously that particular noise becomes so much that it converts a negative signal to positive signal, or a positive signal to negative signal. That means those levels will be effective, which are capable of, you can say, converting positive as negative and negative as positive. And so if you look at this particular, my signal, let's say I'm defining my signal power as Vt upon tau. Okay, so this is my Vt upon tau. Now when this Vt upon tau can be problem, you can say, corresponding to, I mean, all these noise which are above this level, they can produce problem. Understand? Not, I mean, this particular region of the noise cannot produce, you can say, corresponding to this problem. How? I can, calculate mathematically. My probability of error will be Vt upon tau. Okay, Vt upon tau is this particular threshold level. I mean, corresponding to my output, you can say, signal power or output signal level. Vt upon tau. Now you can say, integrate it from this level to infinity, because this particular noise, I want to know about what is the effect of this particular noise power on my probability of error. So my Fn0t, Dn0t, if I, this basically noise, I'm trying to integrate this particular, I think tail, I think you know about Q functions also, Dn0t. And if you take this, this particular, what I'm writing for Fn0 is, simply this particular, you can say, distribution function, Gaussian. Now, if you do that, defining, I mean, I can, now how do you simplify this particular, you can say, expression? So what I do is I define a x as a variable in terms of N0t upon root 2 sigma 0. And so what my P comes out to be 1 by 2 upon root 2 pi x. I'm varying, you can say, x value now becomes V upon, I mean, I think limits change, you have already done this mathematics, I think, probably. So this particular, I mean, if you change the limit, since you have changed the variable here, from, you can say, T2 corresponding to this dn0 T2, or in terms of n0 T2 x. So now this particular becomes x to infinity, and e to the power minus x square dx. Understand? E to the power minus x square upon dx, they are, as I said, I think in the class also, like, they are called, I mean, some sort of definite integrals. So this is a complementary error function. Okay, this e to the power minus x square dx, this is complementary error function. What is complementary error function? Which is, you can say, complement to corresponding to error function. So 1 minus, you can say, error function is your complementary error function. So this complementary error function gives me output as v t upon tau. Okay. So what I essentially I write, as you can say, I can take this v inside, so this becomes v square t upon tau 1 by 2 under root, I mean this value. And now this particular v square t is what? My power. Okay, you understand? So this becomes my power upon eta. Eta is my noise power. So essentially, as I said earlier on, this S is symbol power. S stands for symbol here. It can be bit also. If it's a 1 bit, you can define it as EB also. So this is my complementary error function. So that means my probability of error for a baseband transmission system, which is, you can say, affected by the noise, can be characterized mathematically by calculating this probability of error as 1 by 2 complementary error function Es upon eta to the power 1 by 2. Now look here, I am plotting this property. Suppose my Es upon eta 0, x-axis I am plotting Es upon eta. That means if Es upon eta increases, how does this my probability of error varies? Many of you might have done in programming in MATLAB also. So I'm plotting on vertical axis my probability of error P, understand? And on the x-axis my signal, this particular Es upon eta. That simply as what the power you are transmitting corresponding to your 1 bit or 1 symbol. Okay, so look here, P decreases rapidly as Es upon N increases. If you increase the power level, that means the more power you transmit, the less chances of error are there. That's logical, I think. The less power you transmit, the more chances are for error. So if you look at here, if you transmit, let's say 2 dB power here, so the error will be something here 10 to the power minus 2, you can say, corresponding. Okay. And I mean, if you look at the lower side, if you are transmitting, let's say 0 dB, then the power corresponding to, I mean, if you look at corresponding to this Es upon eta 0, the power corresponding to error for this particular value would be higher. Yes. So that means if I keep on increasing my power, look here, I mean, if I keep on, look the scale. You might be a little bit, getting confused with this scale. So, but the scale here is, you have more power, you can say error here. So 10 to the power minus 1 is more error than 10 to the power minus 5, because 10 to the power minus 5 is obviously 0.00001. That means more the power, less the error. Less the power, more the error. Is it clear? So more power if you can give to your signal, that's a logical also. You can see that, sir, if the losses are there and everything taken into account, still some power will be delivered to the receiver, which it can easily, recover back. So this is, the particular, you can say, a simple relationship between transmitted power and the, you can say, probability of error introduced by the noise. And these calculations will be, you can say, all through your communication, anywhere you might be studying about this particular graph or this particular variation will be always studied. So I mean, this probability of error keeps on. Now look here, if I have 2 bits, you can say, corresponding to, where do I make my decisions, optimum decisions? Okay, that we will study tomorrow. Okay, optimum thresholds. Yes, any question? Yes, please, students. And as you can see on the this particular slides itself, they are from the all this particular you can say content is from Taub and Schilling. That's McGraw-Hill book publications. I told in the class also, TAUB Taub and SCHILLIS Taub and Schilling. The title is some principles of communication systems or something. I think if something is not clear, you can go through that, and then we can again discuss that same thing. Is it fine? Yes, students, or we can continue. You have next class? Okay. So we finish the class now, or I can continue?
Thank you, sir.
Okay.